This is the last standard of the third marking period, Momentum 5, and you are trying to figure out two things. One, you're trying to figure out the acceleration of an object. The acceleration is the speeding up or slowing down of something, the rate at which it speeds up or slows down. Secondly, you're trying to find the force required to accelerate such an object, because things at rest will stay at rest, right? This pen will stay at rest. I need to apply a force in order to accelerate it. Okay, so there are a few equations that we're going to be working with in this unit. I have given you 4. You will have these 4 for your standard. No need to memorize them. But how to use them is important. So let's look at this situation. This was the lab that you guys did a few weeks ago. This is my car, and we went outside and we pushed the car 5 meters. We took some data, right? We took some data on this car pushing, and we found that the time it took to push my car about 5 meters, let's say, I'll be generous and say it was about 2 seconds, even though it was probably more like 2.5 seconds. So the car starts from rest and it rolls 5 meters because you guys were pushing it, remember? And you pushed it for 2 seconds, causing it to move 5 meters. Well, what other information do we know? Well, if it starts at rest, the initial velocity must be 0 meters per second. And the final thing we know, because we measured this out and set this as a condition, we know that the distance traveled is 5 meters. Those are the 3 things we know. And we are looking for step 1, the acceleration, A. What is that? Okay. So this is the part after I have 3 pieces of information labeled and 1 with a question mark. Now I can take these and go to my equations. It's important that I have 3 knowns and 1 unknown. I'm going to look through my equations and see which one can fit these here. Let's go systematically from top to bottom. Okay, could I use this equation to solve for acceleration? Well, it does have acceleration in it. That's great. It does have time, and I have time. Oh, it even has initial velocity, so I have that. Do I have final velocity? Do I know the speed of this car after it moves 5 meters? No, I don't. So I can't use that because it has VF in it. Let me write this down here. VI is initial velocity. VF is final velocity. A is acceleration. T is time. And D is distance. I don't know the final velocity, so I can't use that. And we should immediately see in the second one, I couldn't use that one either because I don't know VF, though I know VI and D, and I want A in the equation, but I just can't use this because of VF. I go to my third one. Well, I have distance, I have initial velocity, I have time, I want A in the equation so I could solve for it. I have time. This one looks like the one that I'm going to pick out. So let's write this out. I'll even use some more paper down here. Let me rewrite my notes. I know T is 2 seconds. I know VI is 0 meters per second, and I know that the distance traveled is 5 meters. And we picked out this one. We said distance is initial velocity times time plus 1/2 AT squared. Now I can plug in my knowns to this equation. Ooh. A equals question mark. Well, the distance is 5. My initial velocity is 0. My time is 2 plus 1/2. A, I don't know A, but I need it in the equation to solve for, so I'm going to keep it there. And time is 2. Remember, this is squared. Okay, so now I can start working through this. Well, 5 is still going to remain over here. 0 times 2, well, that's 0, so this term cancels out. And what I'm left with is 1/2 A 2 squared, 2 times 2 is 4. I could also reduce this even more and say 5 is equal to 4 divided by 2, or 4 times 1/2. That's 2, and A is still over here. Now, I am trying to get A all by itself. That's been the goal along this entire algebraic expression. Get A by itself. So now I can just divide by 2. And I get an acceleration of 2.5. The units for acceleration, meters per second squared. Look at that. I am halfway through this problem. I found the acceleration. Check. Okay, now I have to go back to this car and me pushing the car. Or you pushing the car, really. And draw a free body diagram. A free body diagram of the car. There are a couple forces acting. Actually, there's 4 forces acting on my car. There's gravity acting down, and there's this normal force pushing up. The ground pushing back up on the car. You're pushing with an applied force to the right. And if the car is moving that direction, we could expect that there's some frictional force to the left. Those are the forces acting on my car. The last part, in order to solve for the force, is to use F net equals ma. This is the net force, or the sum of all your forces is equal to mass times acceleration. Look at this. We just solved for acceleration. We just solved for mass. So we can figure out the net force. But our ultimate goal is to figure out the force required to accelerate this car. And the net force is not the same thing as the applied force. Look at that. We're after this applied force. We want to know how strong we push this car to get it to accelerate 5 meters. But in order to do that, we need to take into consideration all of the forces acting in this x direction, in the horizontal direction. Because both of these will cancel out, Fn and Fg. So we don't really care about those, but we do care about Fap and force of friction. So if I'm writing my equation for F net, it looks like this. Fap minus the force of friction, because they're going in different directions. If they were going in the same direction, if I had something where there was an object and 2 forces were going in the same direction, then I would add those 2 up in order to get the net force. But because these are going in opposite directions, I subtract the force of friction from my F applied to get my total net force. It's like if I was pushing on this pen with 10 newtons and you were pushing on the pen with 5 newtons, the overall net force would be 5 newtons that way. 10 minus 5. Okay. So now we have enough pieces in order to solve for Fap. Here are my pieces. So let's try and do this. Why don't we? F net is equal to ma. I could solve for this because I know the mass of the car is 1400. I know the acceleration is 2.5. And now I'm plugging things into my calculator. And I get that the net force is 3,500 newtons. Now this goes into my net force expression. 3,500 newtons is equal to Fap minus force of friction. Almost there. I just need to consider what the force of friction is. And I've been giving it to you. The force of friction acting on this car has been 50 newtons based on how the tires are rolling and how the tires are interacting with the road. So we can just plug that on in. and get 3,500 equals, I'm just going to use the number and not the unit right now, F app minus 50. Well, how do I get F app all by itself? 3,500 equals F app minus 50. Well, I have to add this term to both sides. I'm going to add 50 to both sides so that it cancels out here, and I'm left with 3,550 equals F app. So the total force that someone pushed my car with was 3,550 newtons. That is Momentum 5 in a nutshell. Or not a nutshell, because this video was 10 minutes and 50 seconds long. Alright, see you guys soon.